Deep inside the adult brain's subgranular zone, neural precursor cells are actively dividing. The brain continuously generates thousands of new neurons every day, but the baseline survival rate for these new cells is remarkably low. Roughly 50% of them will naturally undergo apoptosis, dying off within their first few days of existence. The cohort of cells that does survive faces a long road. They spend the next several months slowly differentiating into mature granular neurons and physically integrating into the local circuitry of the hippocampus. Because the hippocampus is the brain's processing center for spatial and episodic memory, the standard hypothesis in neuroscience was straightforward. Acts of learning and memory formation should trigger a uniform increase in this neurogenesis. This visual comparison of the published literature shows why that hypothesis fails. On the left, we see studies where environmental enrichment produces a clear upward trend, upregulating neurogenesis. But on the right, specific spatial learning tasks show a distinct downward trend, actively reducing the number of new neurons. The data presents a strict paradox, indicating that learning affects new neurons through a mechanism more complex than simple growth stimulation. When researchers run rats through the Morris water maze, a standard test for spatial navigation, they find a strict inverse correlation between the number of new neurons and the acquisition of spatial memory. The animal cohorts exhibiting the lowest number of adult-born neurons after training actually demonstrate the most optimal execution of the maze. This reduction in cell count is not a byproduct of physical exertion. Control groups show that the targeted cell death is driven specifically by the cognitive act of acquiring the spatial map, rather than the physiological stress of swimming or the repetition of the training itself. Looking at total cell populations across the entire hippocampus masks the mechanics of the learning event. The overall number drops, but that top-line metric hides what is happening to individual cells. Adult neurogenesis does not operate like a cognitive volume dial, where more neurons guarantee better memory. To understand the mechanism, we have to isolate the exact developmental phase of a neuron at the exact moment a learning event begins. This timeline tracks Dupre's study, proving a learning event's effect on a new neuron is dictated entirely by its age on day 0. First, population A, neurons born 7 days prior, extending short dendrites. Next, population B, younger cells born 3 days prior. During the initial acquisition phase, the animal learns rapidly, rescuing population A. Because population A is mature, it establishes synaptic connections, locking into the circuit. But that same phase is lethal to younger cells, inducing active apoptosis in population B, dissolving them entirely. Learning acts as a specific temporal filter, dictating survival or death based strictly on developmental maturity. This dynamic is called selective stabilization. It is a precise neural editing process, akin to the pruning that happens during early childhood development, and it is entirely distinct from random generalized cell death. We can map this pruning directly to the progression of the Morris water maze. Training is divided into 2 phases, beginning with initial acquisition. The acquisition phase is defined by rapid behavioral improvement. Biologically, this rapid mapping correlates precisely with the targeted apoptosis of the youngest 3-day-old cells. Once the animal knows the maze, it enters the asymptotic phase. Performance plateaus, shutting off the apoptotic signal and instead triggering a massive increase in the proliferation of new precursor cells. The dentate gyrus uses the distinct phases of learning as discrete signals. It alternately clears out uncommitted cells to sharpen the current circuit, and then triggers the next wave of biological hardware for future memory tasks. To test if neurogenesis is strictly dependent on the hippocampal circuit, researchers shift the testing model away from spatial navigation and into classical conditioning. In delay conditioning, an animal associates 2 stimuli that physically overlap in time. Because they overlap, the brain doesn't require the hippocampus to process it. Trace conditioning introduces a temporal gap between stimuli, requiring the hippocampus to hold the memory trace. Mastering it significantly increases adult-born neuron survival. But delay conditioning, a task of similar difficulty with overlapping stimuli, has 0 impact on neurogenesis. The trend line remains completely flat. If an animal is first trained in delay conditioning, a subsequent trace conditioning task can become independent of the hippocampus. When that happens, the survival effect on new neurons disappears entirely. Mastering a task is only relevant to neurogenesis if the cognitive demand requires processing within the hippocampal circuit. To prove a causal link between new neurons and memory function, researchers use targeted ablation models, methods designed to selectively delete the new neurons entirely. One method uses the chemical AM. It targets dividing cells, eliminating only the very youngest precursor cells, leaving partially mature mid-stage cells intact. Targeted irradiation is different. It permanently eliminates the entire population of adult-born neurons, both the youngest precursors and mature integrated cells. The result of both ablation methods is counterintuitive. Animals subjected to this targeted deletion often perform perfectly normal spatial learning in standard water maze tests. The existing fully mature networks within the CA1 and CA3 regions of the hippocampus possess enough inherent plasticity to compensate for basic spatial navigation tasks. If the brain's existing architecture handles standard spatial mapping without new cells, the true computational function of adult neurogenesis must be highly specialized. To break the ablated dentate gyrus, researchers rely on a stress test, the radial arm maze, configured for high spatial interference. Ablated animals navigate easily when cues are distinct. They fail exclusively when spatial cues overlap heavily, a scenario requiring the brain to distinguish nearly identical events. This process is pattern separation, transforming highly similar inputs into distinct neural representations. Young adult-born neurons are highly excitable and fire more easily than older cells, making them the exact computational units required to execute this data separation. Selective stabilization guarantees the brain a constant supply of these uncommitted, highly excitable units, precisely when environmental interference is at its highest. Binary metrics asking if a task increases or decreases cell count fail to capture the reality of the hippocampus. The literature requires a deep analysis of temporal interference and exact task demands. The dentate gyrus employs this cycle of production and selective pruning to provide the specific computational units needed for high-resolution pattern separation.